Welcome to The Explainer. Today, we're diving into something pretty amazing: how we teach machines to see in 3D. We're going to break down exactly how a camera, a device that only sees in flat, two-dimensional images, learns to understand depth, distance, and orientation with incredible accuracy. You ever play with an AR app on your phone? You point it at your living room and bam, there's a virtual dragon just hanging out, and it stays perfectly still, even when you walk around. Well, it all starts by solving a really fundamental problem that every single camera faces. Right, so let's get into the nitty-gritty. How in the world does a flat 2D picture from a camera turn into this rich 3D world that a computer can understand? This is the core problem, and it's really the foundation of all computer vision. Here's the thing you've got to get. A camera doesn't really see like we do. It doesn't understand depth at all. To a computer, a photo is just a flat grid of colored dots. A giant skyscraper way off in the distance could look the exact same size as a little toy car sitting right in front of it. All that spatial information just gets flattened out. So how do we fix this? Well, engineers use this really elegant idea called the pinhole camera model. Just think of it like this. It's basically a math formula that traces how light from a 3D object travels through a single tiny point, like a lens, and hits that flat sensor. It's our first step in translating those 2D pixels back into 3D coordinates.
Okay, but there's a catch. That pinhole model, it assumes you have a perfect camera. And let's be real, in the real world, there's no such thing. So before we can calculate anything accurately, we have to teach the camera how to correct its own eyesight.
This whole process is called calibration. And honestly, the best way to think about it is like getting a brand new pair of prescription glasses for your camera. It's all about creating this mathematical fix for all the weird little distortions and imperfections in its lens, making sure that what the computer sees matches what's actually there.
And this slide is a perfect example of what I'm talking about. See how the straight lines get all warped? You've got barrel distortion, which makes everything bulge out like a fisheye lens. And then there's pincushion distortion, which kind of squeezes it all in. Now, imagine you're a self-driving car trying to read a lane marking. That little curve could be a really, really big problem. Calibration is what straightens everything back out.
So how do we actually do this calibration? It's surprisingly simple, really. You just show the camera a pattern that you already know the exact dimensions of, like this classic checkerboard here. Then an algorithm finds the corners in that warped image and compares them to where they should be. From there, it just builds a little correction map to fix that error on every single image it sees from now on. Pretty clever, right? All right, so our camera's vision is now crystal clear. But that's only half the battle. How does it actually figure out where something is in 3D space? And just as important, how does it know how big that something is? Well, the answer is pretty simple. You give the camera something it can measure against. You literally give it a ruler for robots, if you will. These are called fiducial markers, and they're like these little anchors in the real world that a computer can just instantly lock onto. Yeah, these markers are what we call a ground truth. Because the computer knows the marker's exact size and its pattern, it can instantly calculate its own position relative to it. And this gives it what's known as a 6 degrees of freedom pose. Now, what's that? It means it doesn't just know its X, Y, and Z position, it also knows its rotation, pitch, yaw, and roll. And that complete understanding is the secret sauce to any kind of high-precision tracking. And you can really see the evolution of these markers on this slide. We started out with simple, flat things, right? Like that checkerboard we saw earlier. Great for basic calibration. But for the really complex stuff, like advanced robotics, where a robot arm needs to know its orientation from any angle, we've moved on to these volumetric targets. They're basically 3D objects just covered in reference points. And to make these systems even better, researchers build these incredible hybrid testing setups. You can see it here. They're capturing video from a real camera tracking a real object, but at the exact same time, they're running the same scenario in a perfectly simulated digital twin. This is so cool because it lets them compare the results side by side and figure out, hey, is this error coming from my software, or is it just because of some weird lighting in the real world? But markers have a pretty big downside, don't they? You can't just go around sticking them on everything everywhere. So, what happens when a robot has to navigate the real, messy, uncontrolled world? This is where a really powerful technique called SLAM comes in. It stands for simultaneous localization and mapping. And trust me, this is the magic behind basically all autonomous navigation. We're talking everything from self-driving cars to those little robot vacuums that clean your floor. It's how a device can build a map of a place it's never seen before while figuring out where it is on that map at the same time. Now, SLAM isn't just one thing. It's a whole family of different techniques. You've got some of the older methods that use a lot of statistical guesswork to predict where the robot is going. Then you've got newer approaches that use deep learning to recognize features in the environment. And some of the most popular systems today, they basically look at all the visual data at once and solve this giant, complicated puzzle in real time to find the single best answer for where the device is and what the map looks like. It's pretty wild. Okay, so we've got tracking with markers and tracking without them using SLAM. But what's the difference between tracking that feels, just okay, and tracking that feels perfectly real, perfectly stable? When it comes right down to it, truly high-quality tracking is this really tough balancing act between three key things. First, you need accuracy. I mean pinpoint accuracy. Second, you need stability, so the object doesn't jitter all over the place. And third, all of this has to happen in real time, instantly. Any lag, any delay at all, and the whole illusion is just shattered. And this table gives you a fantastic real-world look at that balancing act. At one extreme, you have something like OptiTrack. This is the stuff they use for Hollywood special effects. You need a whole room full of cameras, but you get insane, sub-millimeter accuracy. Then, on the other end, you have something you can buy off the shelf, like the Vive Ultimate Tracker. It works anywhere, no extra setup needed, but your margin of error is a bit bigger. It's that classic trade-off, right? Are you going for ultimate precision or ultimate convenience? And you've got to remember, this isn't all about the hardware. The real world throws a lot of curveballs. Bad lighting, moving too fast, something getting in the way of the camera. Heck, even just moving too far away from where you started can all mess with your tracking precision in a big way. But this all leads us to what's next, the future of tracking. And it tackles one of the biggest issues with markers head-on, the fact that they're often pretty ugly and really distracting. I mean, what if we could have all the precision of a marker, but you couldn't even see it? Okay, this is where it gets really cool. Researchers are developing something called eye markers. They're made from these special materials that only reflect light that we humans can't see, like infrared or UV light. So to you and me, a wall with an eye marker on it looks totally normal. But to a robot with the right kind of camera, it's like a bright, shining beacon. This kind of technology really opens the door to a future where our physical world is just seamlessly blended with digital information, without any of that ugly visual clutter. It's the next big step towards true augmented reality. And it kind of makes you wonder, doesn't it? What will we see when our machines can see things that we can't?